So moving forward, Dr. Philip Metzger is going to give a presentation on quantifying engine exhaust ejecta from landing large spacecraft on the moon. So Philip, feel free to take over the screen whenever you are ready.
Okay, let's see if this works. Do you see my charts?
Yep, I can see
it.
your screen and we hear you just fine.
Awesome. Okay, I'm going to be talking about quantifying engine exhaust when a large lander lands on the moon. This is based on about 20 years of research. It's going to be an extremely top level overview. So the phenomena when you look at a landing like an Apollo lunar module, these are images looking out the window from one of the lunar module landings. The primary phenomenon is that the rocket exhaust is scouring the surface and blowing ejecta particles away as a dispersed flow. However, at the very end of the landing, we did see bursts of dense clods of material, large clumps of material blowing out en masse. So we know that scouring the surface is not the only phenomenon that occurred, even with a lander about 8 tons like the lunar module. So when you go to larger landers, like a 40-ton human landing system, there may be deeper cratering phenomena. But because we have to peel this onion away one layer at a time, this talk is going to focus just on the scouring phenomena and try to quantify that. We do also see rocks blowing during the lunar landings. In Apollo, there's a rock that's the size of your fist going 60 miles per hour. We have evidence about the damage that this can cause from Apollo 12. The lunar module landed 160 meters away from the old Surveyor 3 spacecraft. The astronauts cut pieces off like that camera you see in the middle, and then the right-hand picture is the bottom section of the camera. Coupons were cut out. I had several of those coupons in my lab for several years. We had a team of people analyzing them. For example, the left is the paint as it was protected underneath a washer, and the right shows the paint after it was sandblasted by the Apollo lunar module. And there's lunar soil mixed all in the paint. There's a crack you can see running through the paint. Those cracks look like a dried mud cracking pattern. A lot of the junctures where the cracks meet, there are cylinders where a lunar sand-sized particle was embedded into the paint. This is a laser scan on the right. It's inside out, but it shows one of the pits where a sand particle penetrated into the paint, and these ridges running away from it are the cracks that radiated away from the pitting. Now, the damage was pretty extensive, but it would have been 1,000 times worse if the Surveyor had been 1 meter higher. It was down in a crater, and most of the ejecta went right over it. So only about 1 part out of 1,000 that was scattering out of the sheet actually hit the Surveyor. Nevertheless, it was complete coverage. This is a shadow that was etched into the Surveyor by the sandblasting. It's the shadow of a bolt that was here that has been removed. And you can see by the completeness of the shadow that it was a complete scouring of the entire spacecraft. And also there's no penumbra. That gives us information about the particle scattering. Okay, so now this is more recent work. This is a video that I just completed with Jim Mantovani at the Kennedy Space Center. This is the result of a 40-ton lander landing on the moon. This light circle is the moon. You're going to see the ejecta blowing out. This is faster than real. In real life, it takes about an hour for the ejecta to go all the way around the moon. But you can see the ejecta does blow globally on the moon. It deposits all over the entire globe, and it continues to rain in for weeks after a 40-ton lander lands on the moon. This is zoomed out, the same simulation. There's the moon. This dotted ellipse is the orbit of the proposed lunar orbital gateway. And so you can see the ejector from a 40-ton lander will blow completely off the moon. It wraps around the moon. This is a cross section. If you want to see the 3-dimensional figure, you would rotate it around the center axis, and that would be the shape of the ejecta cone. But this, I'm going to stop it right here. This is several hours later, and the lunar orbital gateway, if it passes through this point, we were estimating it would sustain about 10,000 impacts per square meter at hypervelocity. These are particles 10 microns and smaller that reach to that altitude. Now, when we try to calculate how much erosion would actually occur, We spent a lot of time analyzing the imagery under the lander. You can see evidence of the erosion, like this is a headed erosional remnant. The erosion is actually more about a meter away from the nozzle because the shear stress is higher there. You can see these strata in the lunar soil where there was a mechanical discontinuity between the layers and it was eroding and it stair stepped down, moving away from the nozzle. And so when you factor all of these features and add it up, it looks like about a ton or two of regolith was blown away. We did a lot of experimental work trying to quantify the erosion rate, including about 450 parabolas in lunar gravity in a reduced gravity aircraft. We did vacuum chamber testing out at NASA Ames. We did testing on volcanoes in the natural tephra. And the end result of all the experimental work is this equation. This says that the erosion rate in kilograms per square meter per second is proportional to the shear stress that the gas puts on the soil divided by a bunch of soil parameters, the density, the gravity, the cohesion. And if you lump all the soil and environmental parameters together, it turns out it's equal to an environmental factor times the shear stress. So if you do these simulations of the landing, you should be able to integrate over the shear stress everywhere and calculate the total erosion. When we do that, it comes out with an answer that's 10 times too high. So something was wrong. We went back and we did more analysis on the landing videos. We invented a method of looking at synthetically adding dust or subtracting dust from the images to create the haziness that we can match from frame to frame. And when we used this method, we came up with a different answer. It told us that the shear stress to the 2.5 power is the erosion rate. So how do we reconcile these? By the way, when we did this method, it predicted 2.6 tons of soil were blown, and that is about right. So I believe this method that was based on the empirical data. Something's wrong with the terrestrial experiments. Well, here's a clue. When we did these experiments out at NASA Ames, if we kept the shear stress constant, but we made the gas increasingly rarefied, as it gets more rarefied, the erosion rate increases. And this is an effect that only shows up when the gas is very, very rarefied. So the erosion rate starts increasing as it gets more rarefied, approaching lunar vacuum. I'll explain this curve in a moment. Now, this is important because a 5-ton lander or an 8-ton lander like the lunar module is in free molecular and transitional flow all the way down, whereas the gas under a 40-ton lander will transition into continuum flow regime. So if there's a transition in the physics, it will make a difference with these larger landers. Now, this is the simplest possible model. When we put all the empirical data together, you end up with a surface that looks like this. The x-axis is the rarefaction, the Knudsen number. The axis back into the page is the shear stress locally on the soil, and the vertical axis is the resulting erosion rate. The left side is continuum flow, matches our experiments. The right side is vacuum conditions. These darker lines are where we took data. You can see there are big areas where we don't have any empirical data. And so this simplest model may not be telling the whole story, but this is what we have so far. If you look at a 40-ton lander, it laps over into these regions that we've never measured before. And when you look at a small CLIPS lander, a very small lander, it's down in the same region that the lunar module was operating. So when we integrate this equation over the landing trajectories of different size landers, the empirical result is that erosion scales as the mass of the lander to the 1.77 power. It's not as bad as we previously thought, but it is still faster than linear. And so here's the answer. If you have a 40-ton lander landing on the moon, it looks like, to the best of our knowledge today, it's going to blow about 98 tons of soil, which is enough soil hard packed to fill an entire kitchen. And so that would cause, we think, about 2,000 hypervelocity impacts every time the lunar orbiter gateway flies through the ejecta sheet, which is twice per orbit on a week-long orbit. We don't know how long until the solar wind and the gravity of the sun and the earth perturb it enough to disperse it. But until it's dispersed, it's going to be getting on the order of 2,000 impacts twice per orbit. A 200-ton lander, which might be, for example, a 100-ton lander with 100 tons of ascent propellant, that would blow about 1,570 tons of ejecta, according to the best theory we have today. So that's enough ejecta to fill a 2-story suburban home, hard packed. And so therefore it would be quite a crater. And that would cause about 32,000 impacts per square meter, twice per orbit of the lunar gateway. So the result is the damage caused by large landers may be severe. This is preliminary work. More work is needed for confidence, obviously. This did not, as I said at the beginning, did not assess the bulk cratering phenomena. Those would likely aggravate the problem. So we do need instruments to measure these effects. We can't do the right experiments here on the Earth. And the final conclusion is we definitely need to develop mitigation methods like building landing pads on the moon. This is a consequence of it being an airless body. Okay, so that's it. Thank you for your attention.
Phil, thank you very much. You do have some questions in the chat room. So I think you almost answered the one from Rodrigo Romo. He said, it seems logical that a landing pad would significantly reduce the ejecta from a lander. Have you calculated or modeled how big does the landing pad have to be to safely eliminate risk to adjacent infrastructure?
Well, that's a work in progress, but I can tell you for a 40-ton lander, we did this, Paul Van Susante and I did some calculations, and we were estimating about a 20-meter diameter, maybe 23-meter, depends on the spacing of your engines. That would be sufficient to avoid all erosion. Obviously, the larger the lander, the larger the pad that you need.
Okay. Ijwal Rout asks, he says, a great talk. What's the lifetime on the impact rate in orbit?
Yeah, we don't know that. Josh Colwell at UCF has a student currently working on that. And so she's doing simulations of the 3-body problem, I guess, Earth and moon gravity with the dust. And then we have a postdoc who's going to put in the solar wind effects, but we won't have answers on that for a few more months at least.
Okay, I think we have time for just one more. Laurent Sibyl writes, do the predicted ejecta masses assume that the large landers use main engines for landings to within a few meters of the surface? What about ejected during launch from the surface?
Great questions, both. So I assumed the trajectory was the same as the lunar module, and I assumed engine cutoff. I think I assumed 1.5 meters above the surface, free falling the last little bit. So if you have the engines mounted higher, it will have a fantastically good effect in reducing the ejecta. That hasn't been quantified yet, but I have done enough work to know that it will be a dramatic reduction. Launching effects, you end up with a shock effect from engine ignition, and that shock effect is dramatically worse than the steady state flow effects, maybe almost an order of magnitude worse for a brief blast. So lighting an engine on the moon for a large lander with the engines mounted low is going to produce a very big blast of ejecta. There will also be acoustic issues. We usually don't think about acoustics on the moon because it's a vacuum. But when you've got that much gas around your lander, especially if you have a multi-engine lander with upward convection between the engines, that will couple acoustics back to the vehicle. So we do need to look at that as well.
Okay, I want to thank you, Phil.